Yeah, just started recording. Hmm. So for our understanding, what are we doing? We have drawn a straight line on XY coordinate, right? I am marking this point, some arbitrary point I am taking X. Okay. Then from here, when the value of this equation, when value is X, this is essentially Y, right? Correct? Hmm? Then let's take another point, which is by adding a small amount, let us say dx, or let me do one thing. Let me take a completely different name for this. Let's take small amount h, and this point is going to be x plus h, right? And then let's evaluate what is the value of y here. This one, right? Now y must have changed by some value. So then let's take this one as y1, this as y2 is equal to what? M into x plus h plus c. Correct? In place of x, I am putting in the value x plus h because we have increased the value of x variable by h amounts. Okay. Now, let me draw a triangle like this. Okay. This part is nothing but h. And then this part is nothing but what? The change in y variable, that is y2 minus y1. Right. Now, if I want to calculate this part, what really is the formula for this? I hope you know that much of trigonometry. If I take this theta value, the angle, then it is like this, right? Tan theta is equal to what? The opposite divided by hypotenuse. So it is essentially y2 minus y1 divided by h, or I can also write x plus h minus x, the same thing, right? So in any triangle, if this is the opposite side and this is the adjacent side, right? Then if I mark this as theta, this particular side we can write, if I take the tan theta of the angle, I will get what? Opposite divided by adjacent. This is the formula that we already have. Make sense? Okay. Now, tan theta has a special significance in any geometrical representation. Tan theta, at least in this situation, we can say, or in this slope intercept form that we are using for a straight line, right? Now, this particular m value, the slope, is actually represented by tan theta. Okay, so essentially what is it? M is equal to y2 minus y1 divided by this x, these two get cancelled out. So divided by, okay. Now this is for the straight line, for this particular straight line, where the slope of the line, the inclination of the line is essentially constant. It is same throughout. Okay, wherever, say for example, you drop in a triangle over here, you calculate tan theta, it is going to be the same. Wherever on the line you calculate tan theta, the slope is going to be constant. Okay. However, if the entity that we are trying to measure is something like this, a continuous curve, in that situation, you cannot measure the slope maybe from here to here, right? Because this line is continuously changing. Make sense? This is the problem that we face. Why? Because if you look at the error function, the mean squared error function, it is a parabola which is changing its value at every point in x-axis. For any x value, two different x values, you take the value of MSE, you get a different value, right? Now, this is the challenge we need to tackle because we understood, okay, this is the slope formula. Okay. And for a straight line, the slope is constant. So we don't have any problems. But the problem over here, when we try to apply the same concept to this one, this curve, the problem is that this particular part is changing continuously, right? If we want to calculate the slope, say for example, x is equal to this point, then here the curve is essentially changing. It is more like an arc, right? And then this difference h does not represent the change in curve at all, right? So in that situation, what we need to do is we need to shrink this h so small that it almost becomes 0. Okay, but not exactly 0. Because if you make h 0, then the math is going to break, right? M is equal to y2 minus y1 divided by 0. Divided by 0 is something the math cannot solve. So we shrink this h to an extent where it almost becomes 0, and conceptually it represents a single point. Okay. When we do that at a point like this, right? Then you can actually draw a tangent on this line. Why draw a tangent? Because the tangent represents what is the slope of that particular point. Otherwise, the tangent has no meaning. Please remember that. All we need to do is to calculate the slope of this point. That is all we are trying to find out. Okay. Because for us, the slope gives in which point we are in this particular graph here. Are we on this side or this side? Correct. If I draw a tangent at this point, say for example, then the slope is actually negative because we are coming down. And if we draw a tangent at this point, then the slope is going to be positive because it is rising. Make sense? And that is what we are concerned about here. Correct? So that is why we reduce h value to almost 0 but not exactly 0, where h effectively represents a point, and at that point we need to find out the change in y2 versus y1, which gives us the slope of that particular point, single point. The entire thing why we need to do that is just because the curve is continuously changing, and if you are not if you are not pinpointing on a single point, you cannot determine the slope at all because the curve is changing one point to another. The curve is different. So one single tangent you cannot draw. That is why you cannot determine the slope in that situation. So what are we doing? We are reducing h, trying to bring it to a point. However, if it becomes exactly a point, then what? H becomes 0, right? X minus x gone, and then h value effectively becomes 0 because length of a point is 0 always, right? In that situation, this case happens. Okay. What the mathematicians previously did as part of the calculus is they used a notation called m is equal to, or you can say, yeah, anything is fine. If f represents this curve, a function that represents this curve, right? Then differentiation of f, that is denoted by f dash or df by dx, okay, is actually equal to, there is a concept called limit. Limit h tends to 0. And here what are we doing? F of x plus h minus f of x divided by, you can relate to this part, right? Why I wrote this one? Effectively, f is a function of x, correct? And what are we trying to do? The difference in 2 points, right? In x coordinate, the difference is represented by h, and when the x coordinate value is x plus h, f becomes what? F of x becomes f of x plus h. That is what I have written here. When I am trying to evaluate f of x at x, then y is what? Exactly f of x. Correct? That difference I am taking. And this is the whole thing about differentiation. Make sense? Do you have any doubts regarding this? Just ask away. If you don't have any doubts, you can also say that. No doubts? Shall I continue? Don't worry, I will connect it with our gradient descent. Just understand how differentiation essentially works. So it is basically telling like this. Okay. How much y is changing this part, right? When I change x from x to x plus h, that is what the slope is. Okay. Now just look at this MSE curve. Okay. Or at all these points, the tangent's slope of the tangent is some value. Here it is negative and here it is positive. this side, right? That is all fine. But look at this lowest point. Here, if you draw the tangent, is completely flat, right? Completely flat means what? It is parallel to x-axis, right? And at this point, the slope of the line is equal to 0. It is laying flat. There is no elevation or depression. Make sense? And this is the point where slope becomes 0. This is the point where MSE is also least, very less compared to all other points. And the idea of gradient descent is to find out this particular. Okay. All right. Now let's talk about the one rule that I told you yesterday is what? Some common derivatives, if we look at, then derivative is nothing but the result of or something that where we are essentially applying the differentiation. Okay. So if my curve x is represented by x square, my f of x is essentially x square. Okay. So then what happens? I told you, just like an MSE curve, it looks like this. Correct. When I do this, on this, if I apply the differentiation, then df of x by dx is equal to d of x square divided by dx, right? This becomes the exponent comes down to the comes to the floor like 2 into x power 1. This is a standard rule. So you can simply memorize it. Or if you want a generalized formula, then it is like this. If f of x is x power n, okay, then df by dx is essentially n into x to the power n minus 1. This is how you just have to remember. This is what happening here also, correct? So this is one important rule. Since this is not a class on differential calculus, I will not be talking about how we arrived at this particular solution. Okay, it's a different story. Just remember this. Cool. Now, just let's take another intuitive example to explain the next concept. What is it? The chain rule. Okay, let's do one thing. Uh, let's do something like this. I have some three wheels connected together, gears, more like gears. One is larger, one is a little smaller, and another is very small. Okay. If I tell you that on one rotation of this wheel, right, in this direction, this particular wheel will turn in some other direction, but we don't care about. But if I tell you that if I rotate the wheel number 1 once, wheel 2 rotates 2 times. Okay. And if I rotate wheel 2 times, or sorry, 1 times, then wheel 3 rotates, let us say 3 times. Okay. Then how many times the wheel 3 rotates if I rotate wheel number 1? Can anybody tell me? You can type in the chart as well. Get first. So the question is clear, I guess. These three wheels are connected, right? If I rotate wheel number 1 time, then wheel 2 turns twice. Okay. If I turn wheel 2 once, wheel 3 rotates 3 times. So yeah, correct. 6 times, right? One rotation of this results in this rotating 2 times. So for one rotation, it is 3 for the third wheel. That means what? For 2 rotations, it is going to be 6. Okay. Now just look at it from a different perspective. Let's make it something like this. Let me call this as U, this as X. Okay. And this to be Y. Okay. Now I want to calculate this rotation. If I write something like this, Y is equal to f of U. Okay. And U is equal to f of, can I write something like this? It is valid, right? Correct? Yeah. So essentially what is y? Y is equal to f of U is equal to f of x. We need to give some different names because both they are actually rotating or the factors are different. So let me do one thing. Let me write this as g of x, some other name for the function g of x. Okay. Then this formula becomes what? F of u is equal to f of g of x, right? Just give me a second. Yeah, sorry. Okay. Now, if I want to find out how y is changing with respect to u, I can take the differential dy by du, right? Correct. Now, however, if I want to find out one more thing, what is it? How u is changing with respect to x, I can take another differential. What is it? Du by dx. Correct. These two things we can simply comprehend. No issues there. But what if I want to calculate the change in y with respect to x, right? How much y is changing with respect to x, the inner function g of x, right? X is affecting g and g is affecting it is more like a propagation effect, right? The innermost variable is affecting the innermost function, and that innermost most function's value is affecting the outermost function, correct? So if I want to find out dy by dx, not du, mind you, please, it is different from this one, correct? How changing the value of x affects my y, outer function. If I want to find out about this, then what should I write? I need to calculate this. That is what we did here. If I rotate x once, how my y is going to change? We found out about this to be 6. What is it essentially? This one rotation affected in two rotations here. Then we multiplied it with what? This one rotation affects it by 3, and this is how we got 6, right? So that is what we write here. How my dy is being affected by du. Okay. And then how my du is being affected by dx. This is what chain rule is, nothing else. Is it clear? Is it clear? Okay. So most of you are clear. Deepak, and Deepak mentioned yesterday. Is he present today? Yeah. Deepak, is it clear? Fine. Okay. Now let's continue. Let's bring this entire concept into our MSc, right? What is the function here? The mathematical formula for MSc? It is nothing but 1 divided by n sigma y minus y cap yi minus yi cap whole square. Correct? Now this is what we called as error, right? This is error. So if I write it in a different way, then what? 1 by n sigma error square. We can write error I, because for every value of y, there is a value of y cap, right? We are squaring it individually and then summing it up. Can I write like this? This is what MSc is. So MSc is essentially is a function of error, right? Now if I take some other name for error square, let me define it this way. Error is a function. What is it? Y I minus yi cap. This is error, correct? And MSc is essentially a function of error that is given by sigma 1 over n error square, correct? Now what is yi here? Let's replace that. So if I write the error formula with the expansion, then error is nothing but yi minus wxi minus b. This is what error function is, right? And error function is a variable. Sorry, error function is dependent on what? These two variables, w and b, right? Correct. Based on the value of w and b, my error is going to change. Correct. So I can write something like error is a function of w comma b. Okay. And MSc is a function of error. If you connect it with this analogy, right? Wheel number 3 are w and b. Wheel number 1 are w and b, right? And error is wheel 2 and MSc is wheel 3. Okay. How this one rotation is going to affect 3 is our requirement. That is what we will do here. How W and B will affect my MSc, right? And to do this, we apply the chain rule. How can I do this? So D error, not error, D MSc by D W comma B. This is what we want, right? How W and B, a change in W and B, how is it affecting my MSc? This is what gives me the required output. What is it? We need to bring MSC down to zero. Sorry, we need to bring this entire term to zero. Don't worry. Let's go step by step. Just note that we need to find out the change in MSC with respect to the changes in W and B. That is all. Now, how do I do this? Using the chain rule, I can write what? DMSC with respect to D error into D error with respect to D W comma B. Make sense? Were able to follow up to this? Vandita said yes. Ananya also said yes. What about others? 3 people, 4. Rajeshwari. Okay. Okay. What about others? Deepak is very quiet and few more. Affan Kazi, then Isfa, then some Kishu Gowda, Kishan, I think. Sharath. What about you guys? Are you able to follow up to this point, guys? Okay, let me continue. Right now, so far we have understood how we arrived at this particular expression. It is going to be what? Uh, so here, if you look at this, what is the function? This one, right? So I will write it down. D MSC by D error is what? Error is simply squared in the expression, right? This one thing with respect to derivatives is if you have something like this d by dx of x square plus 2x, something like this, then you can actually distribute it like this: dx square divided by dx plus 2 into dx by dx. This way you can write, no problem. Okay, since the relationship is linear here, plus and minus, when two variables or two terms are connected in this manner. However, multiplication is a different story. You can't do that. Plus and minus, if you have, you can distribute the derivatives. Okay. And this is what we are actually doing over this as well. In this case also, what is this error I square sigma means what? Individual errors are being added after squaring. Correct. There is a plus sign. It is like error 1 plus error 2 plus and so on. Right. On this, we are trying to take the derivative. What are they? W comma B. Right. I can distribute them over individual errors. So that is fine. That means what? D MSC by D of W comma B is what? D by D of W comma B of what? Entire function 1 over n sigma error square. This I can actually write like this. What is it? 1 over n. It is a constant, right? Can take it out. And then inside this one I can take, so sigma d by d of w comma b of error square. In this manner I can actually write. I'm simply distributing. It is a shorter way of telling, right? I'm applying derivative on each error and then summing it up. That is what it is. Correct. Now, the problem here is we need to apply the chain rule. Why? Error is a function of w comma b, but this MSC is a function of error. It's error square, right? So that is why I will do something like this: 1 over n sigma. For this error square, taking this entire thing as a function, I will apply the rule of exponents. What is this? What is it? It was mentioned somewhere here. Yeah, this one. Okay. So based on that, what do I get? 2 into error, correct? And then error I can write, no problem, right? And then I will have to do what? Multiply the next one. What is it? D error, right? With respect to what? W comma B. This I need to find out. This is straightforward, no issues there. Has it frozen? Yeah, cool. Understood so far? It is what? DMSC with respect to D W comma B. Now the problem here is W and B are two independent variables, right? Then how do we find out this particular derivative? We cannot change W and B simultaneously, right? There's a problem there because both are independent. So in such situations, what do? We simply first find out the effect of W on MSC, okay? And again, we will find out effect of B on MSC independently, okay? And then we put together the result that we get. Fine. So for that, what do we need to do is we will have to take partial derivatives. Partial derivatives. If I have a function of two variables x comma y, okay, then essentially if I want to find out the effect of change in x on f, then what should I do? Keep y as constant. Okay, it is not changing. We are simply assessing the effect of x on f. In that situation, we treat only x as the variable and y variable is treated as a constant. Okay. In the same way, if I want to find out the effect of y on f, then I have to treat x as what? A constant. Okay. That is what we have to do here as well. We need to find out about the effect of w on MSE, and also we need to find out the effect of b on MSE. How to do that? First, we calculate the effect of w on MSE by keeping b value as a constant value. In the same way, we need to calculate the effect of b on MSE, okay, by treating w as constant. And to calculate that, I will write the formula. dw is what I mentioned yesterday. This was the name given. So it is essentially effect of w on MSE. Okay. So how do I write that? To represent partial derivatives, instead of d notation, d by d something, right? For example, dx, we write a different symbol that is called dou, dou by dou x. It is effectively the effect of x variable alone on f, keeping every other variable constant. Okay. So here, now I will take the first partial derivative, that is effect of w on MSE. So it becomes what? Dou MSE divided by dou w is equal to what? The same thing that we have here. Till here it was not relevant, right? But at this point it becomes relevant because the error is the function of w and b. So I will keep this part as it is 1 by n sigma 2 into error, right, into dou error by dou w, only w. That is what we are trying to assess. Okay. So if I simplify this and expand this error, what is error function? So this 2 comes here. I can take it out as a constant value. So 2 by n sigma error of ith term into what is MSE? Sorry, what is error? It is nothing but yi minus wxi minus b, right? It is differentiated with respect to dou w. Fine. What did I tell you? When I am differentiating or when I am finding the effect of w on this error function, I have to treat only w as the variable and b has to be, all other terms have to be treated as constants. So b also becomes a constant. There is no w term in here, right? So effectively what happens? 2 by n sigma error I into this, for this term it becomes 0, right? Which one is it 1 by d w comma d? Which part? W comma b star. This one? Which part? Sorry, I'm unable to get your question here because d messy by d w comma b part, sir. This one? Okay. What seems to be the problem here? 1 over d of w comma b. Where is 1? No. What seems to be the problem here? It is simply d MSC over dw comma b, because we are trying to assess the effect of w and b on MSC. It is nothing but 1 over n sigma. This part we were able to solve, right? This part here, right? Based on this rule, where is it? This part we wrote it as 2 into error I, right? Because error I itself is the function here. It is squared. So the final answer I got 2 into error I power power 1. It is 2 minus 1, right? This part I got, fine. The remaining part is what? D error divided by d w comma b. From here, we are actually switching to partial derivatives because I cannot calculate the derivative with respect to two variables simultaneously. So we are trying to assess two different derivatives. The error how? In this part, okay, very simple. Look at this. If I let me take a empty space somewhere. Now, what is MSE? If I assign a separate name to error, let me make it E. Okay. Now, MSE is a function of E. What is it? It is equal to 1 over n sigma E square, right? But what is E? It is yi minus yi cap, correct? Now, I need to calculate yi cap is nothing but what is it? Yi minus wxi minus b, right? So now error is essentially a function of w comma b, correct? What I am trying to find out here, what am I trying to find out here? The change in MSE with respect to w comma b. So change in MSE with respect to w comma b, not e. We need to apply the chain rule here. Make sense? Okay. Now to do that, what did I do? What is chain rule? I explained it here, right? I don't know how you missed it. See, what does chain rule say? If y is a function of u and u is a function of x, if I want to find out the effect of change in x on y, then what do I have to do? First, I have to find out the effect of u on y and then multiply that effect with effect of x on u. Please remember this example, right? This part is nothing but this part, DMSC with respect to error. Okay. And then this part, error with respect to W comma B is this one. Cool. All right. So far, where have we come? We are trying to find out the effect of just W on MSC, right? This part is clear. No issues there because this is with respect to E function that we have taken here, right? So that is fine. However, this I need to treat B as a constant, W as the variable, right? Now what happens? If I take the derivative, yi is a constant which doesn't change at all with respect to W, right? So the effect of W on yi is essentially 0, right? And then minus W xi. Xi is a constant in this case during differentiation, correct? So let me keep xi as it is. W, what is the formula? This formula, where is it? This one, right? So the same formula, if I apply here, it is going to be what? To 1 the power of W into W to the power 0, correct? And minus B is a constant again. There is no effect of W on B. That is why 0, correct? So this entire term, now if I simplify this, 2 by n sigma error I into what is remaining here minus xi, nothing else. At W to the power 0 is again 1. You multiply that 1 with 1. This is what essentially remains. So again, if I simplify this, if I want, I can take this minus sign outside, right? This is allowed. 2 by n sigma error I multiplied with what? Xi. This is what the effect of W is on MSE. Understood? So this is essentially dou MSE by dou W. This is just a name I have taken. Okay. The same thing we can do for B as well. So dou B, sorry, dou MSE by dou B, let me call it as dB, is equal to what? 1 over n, the same formula. Was it? What is it? Sigma dou by dou B of error I square, correct? Now I need to apply the chain rule once again. What is it going to be? 1 by n sigma. If I do that, 2 into error I, correct? The first part is as it is. Where is it? This part. It is kept as it is. This part we need to solve now. Into dou by dou B of what? Yi minus W xi minus B. Correct? Now in this case, we are treating B as a variable, right? W xi both are constants. Yi is also constant. So this essentially becomes what? Shall I take 2 outside? So it is 2 divided by n sigma error I into the effect on yi is 0 minus effect on this is 0 minus b becomes what? 1, correct? This exponent 1 has come here, b to the power 0. So essentially it becomes what? Minus 2 over n. This minus 1 I'm taking outside. Sigma error. What is this? Dou MSE by dou B is equal to dB. This is what it is. Got it? Yes. If you have any doubts, please ask. If it is clear, I'll move forward. All right. Good. So now, like yi, xi is also constant, then why didn't you mention it as 0? Okay, good question. But if you look at this particular part, right? Where is it? Okay, here it is actually making sense. Our question. Since xi is also a constant, why did you not mention it as 0? Why? Because it is multiplied with the variable that we are trying to differentiate with. So d2x by dx, or let me take 2x square just to make you understand, right? So if this is the case, the result will be, sorry, 1 second. Yeah. So if this is the case, right, the basic rule of differentiation is like this. So 2x square, 2 is a constant that is multiplied with the variable. So any change on x square is multiplied by 2 and then it is distributed over, right? That is why what we can do, we can take this 2 as a common factor and write it like 2 dx square by dx. Okay. And then we differentiate x with respect to x square with respect to x. And then we get what? 2, the previous 2, and then into this 2 into x as the result after differentiation. Okay. The same concept I am applying here as well. Where is it? In this case, xi is a constant multiplied with w, right? That is why I have taken this xi as a common factor here. I cannot put 0. Why? Because it is multiplied, not added or subtracted. Yi, I have taken it as a constant because there is no w term here. It is just a constant term. Got it? Good. Yeah. So this is what it is. Now, in the last class, if you remember, what we did is we tried to take this, okay, and then update our b value or and w value in this equation, right? W and then minus dw, then b is equal to b minus db. Correct? Do you have any doubts now regarding? I hope you understood how we arrived at these two equations and these two equations. Sorry, not this one. So if you notice this, it is a now previously the original y equal to y cap equation mx or wx plus c, right? It was a univariate function, like x was the variable here. And then we shifted our focus to w and b. Sorry, c instead of c, we used b, right? We shifted our focus to tune w and b. And then we kept x as a constant and treated w and b as variables. Now it became a bivariate function. Univariate means only one variable. Bivariate means two variables. Multivariate means multiple variables. Now this has become a bivariate function now, right? So once we do this, we will have to tune w separately and tune b separately. That is why two equations. Okay. How does changing db or how does changing b affects my MSE separately, and how changing w affects my MSE separately. Okay. And that is why two equations. Got it? If the dw value is negative, right? What does it mean? It means we are in this particular MSE curve, we are somewhere in this part, left part. Why? Because our slope is negative, right? Then what do we need to do? If dw is negative, this negative multiplied with this minus becomes what? Plus. So w, it effectively becomes w plus slope. So what are we doing? We are essentially increasing w, right? with respect to W. If dW is negative, right, then we need to move in this direction. Reduce W by one step based on the learning rate, right? Here we actually multiplied learning rate, if you remember. Why did we do this? Just to smoothen the curve. If the learning rate is too large, right, then we may do something like we may jump directly over here by increasing the W value. Possible, right? Correct. In the same way, if the learning rate is too small, then we are multiplying learning rate with respect to dW, right? So the factor in which W increases can become very small and may end up eternity to reach this point. Understood? So finding out a fine learning rate actually gives you uh, a, um, a better performance coming down to zero slope. Since we are multiplying dW with learning rate, that is why even after 1500 epochs yesterday, we were not able to get exactly 1 as the R square value, because every time the slope gets multiplied by zero point 0.2. Yesterday we took LR as zero point 0.2, right? So it is essentially we are taking the 20% of the slope that we calculated, and that much value we are adding to W. That is what we are doing. The slope is too much. The curve always looks something like this. Okay. So when we are very farther away from the zero line or the least point, the slope is very steep, something like this. And then as we come down, the slope becomes lesser and lesser and lesser and lesser and finally becomes zero. This is how it happens. So when the error is too large, then this value becomes larger, and that is why we add more value to W, either add or subtract. So essentially what is happening, if we are at this part, we are adding W and B values. If you are at this point, the slope becomes positive, right? This part, but this positive value now has a negative sign associated. That is why we are reducing W value effectively. So we come from this point by reducing W value, we will come down like this. What is the value of W and B here is what gives us the best R square. Is it clear now? Now, if any one of you have any doubt, you can ask away. Otherwise, we can wind up the session here. Tomorrow, let us build a really nice linear regression model which contains multiple features. More than one feature also we can do. Or let's do something like we have some thousands of values recorded. In the last class, last two previous classes, what we did was we took our own samples, like 5 values, right? And then based taking that as the input, we fit the line. So tomorrow, let's take a real data set. Let's fit a line and see how our line perform. Okay. I will not be covering multivariate or multi-featured linear regression in this class anyway, for this course. It's slightly advanced. Explaining that part requires more time. Since this is more like an introduction, we will stop at univariate. If you have any doubts, just ask away. Do you have any doubts? Any one of you? If you don't, you can actually drop from the meeting. I will wait for some maybe 2-3 minutes.